Last time I showed you this equation. This is Einstein's time dilation and the reason a clock in orbit refuses to agree with a clock on Earth. And before we launch anything today, give me 60 seconds with it because this little formula is about to earn its keep. We have the following four characters in the equation. Delta t is a stretch of time measured by someone standing still. Delta t prime is the same stretch of time as experienced by someone moving. V is the speed between them and c is the speed of light, the universe's speed limit. Now watch the square root. If v is 0, it equals 1. Both observers agree on time. But the moment you move, v square over c square becomes something. The root drops below 1 and delta t prime becomes smaller than delta t. Read that plainly. A moving clock ticks slower than a stationary one. Don't believe it? Let's run the numbers. A spacecraft cruises at 80% of light speed. Earth measures the journey at 10 years. The astronaut's time is 10 times the square root of 1 minus 0.8 squared. 1 minus 0.64 root of 0.36, 0.6. 6 years. The astronaut steps off 4 years younger than everyone who waved goodbye. That looks like something from the Buzz Lightyear movie, but this is just math as plain as day. And satellites don't fly at 80% of light speed, but at 14,000 kilometers per hour. The same equation still bites, but just in microseconds instead of years. Speed makes satellites' clock run slow, about 7 microseconds a day. But weaker gravity up there makes it run fast, about 45 microseconds a day. Gravity wins, so every satellite clock gains roughly 38 microseconds daily. That is the net effect. So engineers did something wonderful before launch. The clock is supposed to tick at exactly 10.23 megahertz. They deliberately mistuned it, slowed it down to, here goes, 10.2299999543 megahertz, so that once relativity kicked it up there, it would drift into perfection. So the clock was built wrong on Earth, so it could be right in space. They succeeded in fixing the sky, but there was one clock they could never touch, and it's in your pocket. A satellite carries an atomic clock worth more than a house. Your phone carries a quartz crystal worth a few cents. And GPS is the game that punishes cheap clocks brutally. Radio signals travel at the speed of light, about 30 centimeters every nanosecond. From orbit, a signal reaches the ground in roughly 67 milliseconds. Position is just travel time multiplied by the speed of light. So every timing error becomes a distance error multiplied by the fastest thing in the universe. If your phone's clock is off by 1,000th of a second, an error a quartz clock makes casually, your position is off by 300 kilometers. Your phone wouldn't put you on the wrong street, it will put you in the wrong country. And no, we can't just give every phone an atomic clock. Too big, too expensive, too power hungry. Hardware has no answer to this, remember that. But wait, how does your phone even measure that travel time? It's not like the signal arrives wearing a timestamp wristwatch. The answer is one of the cleverest tricks in engineering: code pattern matching. On a universally agreed schedule, every satellite broadcasts a specific pattern of zeros and ones, a pseudo-random noise code. Here's the key. Your phone knows the schedule too and generates the exact same pattern at the exact same moment internally. The satellite's copy has to physically travel down to Earth about 67 milliseconds of flight, so when it arrives, it's late. Your phone's own copy has already moved on. The received pattern is a ghost from milliseconds ago. So your phone takes its own live pattern and shifts it backward, sliding it until the peaks and valleys of both patterns lock together perfectly. The size of that shift is the travel time, measured and not guessed. Embedded in the broadcast is a data packet stating the exact moment the pattern sequence started. So the phone knows when it left and the pattern shift says how long it flew. Travel time times the speed of light, distance to that satellite. But we still have a problem. That measurement is only as good as the clock doing the measuring. And we've established that your clock is a cheap liar. Every distance your phone computes is contaminated by the same unknown clock error. Engineers even have a name for this polluted measurement: Pseudo ranges, fake distances. Here's where the story turns. Engineers stopped trying to fix your clock and surrendered to it. In the words I write in my own notebook, your phone switches from using absolute time to algebra. If we can't know the clock error, fine, call it an unknown. Now the phone is solving for 4 things: longitude, latitude, altitude, and clock bias. And mathematics has a strict price for unknowns. 1 equation each. 4 unknowns, 4 equations, 4 satellites. That's the answer to the question this whole video is built on. Geometry says 3 satellites should be enough to pin a point in space. The 4th satellite isn't there for geometry. It's there because your clock can't be trusted. An algebra is cheaper than an atomic clock. Each satellite contributes 1 equation. The distance formula in 3D equal to the speed of light times the measured time, corrected by the same unknown bias. Write it 4 times, once per satellite. This is the system your phone must crack. Now look closely at those equations. See the square roots wrapped around our unknowns? That word matters more than any other in this video. Non-linear. Every trick you learned in school for simultaneous equations, substitution, elimination, dies right here. Pre-launch, this was a genuine crisis. A receiver must solve this system fast, forever, on weak hardware. There is no formula. So the engineers reached 300 years into the past to Isaac Newton. Newton's method solves the unsolvable by refusing to solve it directly. Step 1. Guess. Deliberately, confidently wrong. Step 2. Ask the equations how wrong and in which direction. Step 3. Replace the curved problem with its flat shadow at your guess. A tangent, and solve that, because linear problems are easy. Step 4. Repeat. Watch it happen. Start the guess at the center of the earth, maximally, absurdly wrong. Iteration 1, we leap thousands of kilometers. Iteration 2, hundreds. 3, down to meters. 4, your street. Your phone runs this ritual roughly every second you navigate. And here's a twist hiding in the solution. The system solves for t as well. Your phone doesn't just learn where it is, it learns exactly how wrong its clock was. Which means, in the words from my notebook, solving these equations gets your phone as accurate as the expensive atomic clocks of the satellites. Position was the mission. Atomic time comes free. Step back and look at what your phone is really doing. Guess. Measure the error. Step toward less wrong. Repeat until the error is tiny. That loop is not just GPS. It's actually the same mathematical soul that trains artificial intelligence. When a machine learning model learns, it guesses, measures its error, and steps downhill millions of times. Newton would recognize it instantly. That's the story I'm telling next. The math that decides what you watch. Because the algorithm that recommended this video runs on the same idea, and it has already turned you into a column of numbers. I don't just teach mathematics, I show you why it works.